Hello, everyone. My name is Nishtha Jain. I'm a research engineer with the ADAPT Center, and I'm here to present our paper, Generating Gender Augmented Data for NLP. The paper was also contributed towards and co-authored by Maja Popvic, Declan and Eva Vanmassenhove. I'm going to walk you through the business problem that we were trying to address in this research work, our final approach. How did we end up gathering data to experiment and implement that approach? And finally, the neural rewriter, which is our proposed solution, and how it was augmented and its performance was improved using a gender classifier, along with some notes on its evaluation, including automatic and qualitative manual inspections. As we can all agree that gender bias is a frequent occurrence in NLP-based applications, and it's especially more pronounced in gender-inflected languages. It can appear through the associations of certain adjectives and animate nouns with the natural gender of the referent, but also due to unbalanced grammatical gender frequencies in our data. This bias is more evident when generating conversational utterances, since the gender would not necessarily be specified within the sentence. And that's because most NLP applications these days are built on sentence level context. Hence, as a step towards more inclusive NLP, our paper proposes an automatic and generalizable rewriting approach by leveraging a neural rewriter for short conversational sentences. We'd like to highlight that in this paper, our main focus was on the Spanish language, since this research was carried in collaboration with Microsoft Dublin, while keeping a specific application in mind that suggested responses in Spanish. Uh, the two very pronounced applications of our proposed solution is as a post-processing step one, to create more gender balanced outputs, and two, to create gender balanced training data, which can help learn our NLP models better in the current age and help in mitigating the bias there. As I mentioned that the language and focus for this research paper was Spanish, but while developing the approach, we kept in mind that the linguistic tools and knowledge were at a minimum so that it was easily applicable to other languages. Just a few examples of the kinds of sentences we were dealing with in Spanish over here that were sourced from the Microsoft data. One was grammatical agreement with gender of a person. There were sentences that had grammatical agreement with with the gender of an object, and there were some sentences that had gender bias due to some social norms. Our approach at the moment doesn't discriminate between human reference and objects. It's furthermore limited to generate only binary gendered alternatives at the moment. But I'd like to highlight that our team was aware of the importance and challenges of tackling non-binary gender as well. And we aim to tackle this in the future work. So quickly walking through the three-step approach that we proposed, where the first one is to gather a big enough corpus of gender parallel data. For this, we identified first the sentences and segments that should have the opposite gender variant for some words. Such POS sequences were then used to extract segments from the huge open subtitles corpus. The next step was to create gender parallel data, which was done by applying a rule-based approach on the POS sequences defined painstakingly in the previous step. And last but not the least was to train a neural automatic rewriter that could convert from one variant or one gender of the sentence to the another, or leave it as it is if it didn't have to be changed. I'd like to highlight that this last step is what made our approach more scalable and removed any need for pre-processing. And that the first two steps were like a one-time thing that you had to use or apply every time there was a new language family that you were dealing with. Diving a little deeper into why we needed to gather parallel data, it was because we wanted to create an automatic gender rewriter using neural machine translation. And for that, we needed a huge enough corpus that went from masculine to feminine or feminine to masculine or neutral to neutral. For this, we identified certain POS sequences since such data sets are not publicly available at the moment. So we had to create and generate our own corpus as automatically as possible. An example on the right is considering a POS class, for example, of clitic pronouns. among other POS classes defined as adjectives and past participles, which show gender agreement in Spanish. So the first column over here basically lists sentences that have that contain pluric pronouns and had a POS sequence like that should be regendered. And the second column denotes how these sentences were supposed to be regendered once the POS sequence was identified. Such tables were created for all the POS classes and for neutral as well as regenderable segments in order to be sure of what we were tackling or what we were training the neural rewriter on. Next was next, since as you mentioned in the last, as you must have seen in the last slide, that we only had a few thousand segments from Microsoft. And that wasn't enough to train our neural rewriter. So we downloaded a huge corpus from the Open Subtitles dataset. We did some basic filtering on it and extracted sentences with less than equal to 10 words, and then POS tagged them using tree tagger. This was done so that we could extract exactly those sentences that matched relevant POS sequences as described in the previous slide. We applied rules on the sentences that had POS sequences matching regenerable sentences using certain rules to create the variants. And then we joined them in both regendering directions so that we didn't include any bias in our data set. Doing all of that, we were able to source a data set of about 2.2 million sentences, of which we used 1,000 sentences for development and 3,000 for tests. This was called the test set from Open Subtitles. Now, to test that approach on the Microsoft data, we also created two different data sets called structured test 1 and unstructured test 2. As the name suggests, structured test 1 was something where the set of sentences matched the relevant POS sequences that we were tackling for this paper. And unstructured test 2 was tackling everything other than that. So sentences with multiple regenerable words or with animate nouns and things like that. Since we wanted to test how generalizable could our approach be, or could the neural rewriter be once trained. Now moving on to our main approach, which is the neural machine translation system. It was trained on the original sentence as the source and the regendered sentence as the target. And as you can see, for neutral sentences, the source and the target was kept identical. The neutral sentences were added in our corpus in order to enable the rewriter to understand, one, when did we need those variants? And if we did, how could we create those variants? The neural machine translation system was trained using the transformer architecture and Sokai implementation, which uses BPE subword units. In order to run our experiments, we tested three setups for the neural machine translation system. There was one that was the standard NMT, which was trained on parallel data without any tags. The other two were neural machine translation systems with tags, where the tags were N and G, where N stood for neutral and G for regenerable. So if a sentence had a tag N prepended to it, it didn't have to be changed, versus with G, it was supposed to be changed. These tags were implicitly available for the training and development set, since if the sentences were same in the source and target, it was tagged as N. Otherwise, it was tagged as G. But for the test sets, we tested two different versions of this. There was one called NMTT, where the tags were available for the test sets in the sense that they were manually tagged. And this also kind of acts as an upper bound for the performance of neural machine writer with tags. And NMT80, where the tags were unavailable, which is a more realistic scenario. Hence, these tags were automatically generated using a gender classifier, which I'll talk about in the next slide. The gender classifier was a system that was given a sentence supposed to classify it as N or G, which is neutral or regenerable. And in turn, it helped us in creating some automatic tags to test the NMT80 rewriter. It was trained using support vector machine classifier on features that denoted TF-IDF scores of character engrams of length 4 to 7, TF-IDF scores of word grams of length 1 to 3, and morphological information encoded in the sense that the variable was coded 1 if there was a gendered part of speech tag present versus 0. On the right is a table to denote the performance of the gender classifier. And as you can see, the classifier performed exceptionally well in recognizing regenerable sentences with a high recall. However, It incorrectly labeled a number of neutral responses as regenerable, which also deteriorated the performance of the NMT system, as can be seen in the next slide. Here, we're trying to quantify the results of the performance of the automatic NMT rewriter using error rates, which counts the which is a percentage of incorrectly converted words normalized by the total number of sentences. As you can see that the error rates are similar for both in-domain and out-domain tests for the neutral segments. Adding manual tags, however, drastically reduces the error rates, which can be seen in the NMTT column as compared to NMT, which shows the potential of an automatic gender classifier. On adding automatic tags, though, the performance of the NMT on regenerable sentences improves quite a bit. However, it deteriorates its performance on neutral sentences. But that's kind of in line with how our gender classifier performed, and as I mentioned just a few minutes ago. A few notes quickly on the qualitative inspection of errors that were found in the sentences generated by the NMT rewriter. We noticed that the most frequent error in neutral responses mostly consisted of regendered pronouns and adjectives, and adding manual tags did bring down the number of these errors. However, on adding automatically generated tags, such errors sort of increased. Within regenderable sentences, the most frequent error was to leave them unchanged. And as we noticed in the last slide, adding tags, whether manual or automatic, did reduce the number of, did sort of increase actually the number of properly regendered segments at the small cost of addition of non-existing words. I want to quickly spend a few seconds on this slide to show how were the incorrect sentences generated for structured and unstructured sentences. As in the first table, you can see the few sentences for the neutral sentence, the actual sentence was correctly generated when the tags were added. However, it didn't perform so good on genderable sentences. To quickly conclude, the biggest challenge in our research work was to gather a large gender parallel data corpus, which was overcome by a quick in-depth analysis of the data that Microsoft provided in order to identify word classes for which an alternative gender variant should be created. Once that was done, we were able to extract frequent sentence structures from Open Subtitles corpus, which is a huge enough corpus to train the neural machine translation rewriter. And in addition to that, we trained a classifier to automatically identify sentences for which a gender alternative should be provided, and those that should remain unchanged. This in turn made our neural machine translation rewriter smarter when it was trained on a system with tags. Quickly, future work is going to include augmenting the existing parallel datasets with more diverse structures. We'd also like to test more setups for the NMT rewriter, such as using gender-related morphemes or characters instead of byte pair encoding. And we'd also like to improve the performance of the gender classifier and bring it to the potential performance that was shown by the NMT writer with manual tags. Thank you.